Okay, hello. So my name is Stefan. I'm working in the infrastructure team at Improbable. And before we start, this talk is going to have two parts. The first part is going to be about the configuration systems we are using and we have been using until this point. And the second part will be about Playwright, which is meant to be a config system that tries to solve all the problems we have encountered while using the other config systems I will be talking about. So, okay, why not write handcrafted configurations? So we have a lot of configs at Improbable. We are using Prometheus, Kubernetes, Google Cloud and AWS resources, then Nginx and Elasticsearch. And yeah, so if we write configs for all of these things and we won't generate configs, it's going to be expensive to write and difficult to change. So imagine that you have like 10 clusters and 5 or 10 or 15 services in each cluster. You're going to have like number of clusters times number of services YAML files. And if you want to change the CPU limits for one service, you have to change a lot of files. And this can be error prone, you can make mistakes, and if you do this change, you send it for review, and the reviewers, they might miss some things. There is also a lot of repetition, which makes config verbose and difficult to navigate. So if you want to change something, you need to locate where is this thing located. And then when you locate the configuration file, you have to open it, you have to find the exact line you need to change. And maybe you want to change multiple lines. So we don't want to write these config files ourselves. So this is a question. I'm not going to talk a lot on this slide, but just keep this in mind while I'm continuing in the presentation. So I'm going to talk about M4. This is one of the config frameworks, or it's not really a framework, it's a templating language we are using. So a long time ago, we were a really small company, and we needed to move fast. So we still need to move fast, but back then we needed to move fast also. And we have some configs in Prometheus, and there were some repetitions, right? And we wanted to solve this very quickly. And one of our engineers knew how M4 works, so we have started to use M4, and we are still using it. So what it is? M4 is a general purpose macro processing language. So it's like a C preprocessor, but on steroids, too much steroids maybe. Simple things in M4 are simple to do. Like defines in C. So if you're not doing anything fancy, it's fine. But if you do something more complicated, the code gets more complex. And the benefit of M4 is that it's very easy to start using. So when you have a rules file for Prometheus and you want to add some macros there, you just rename the file from service.rules to service.rules.m4. You add some macros, and then our systems will generate the rule files for you and substitute macros inside that file. Okay, so we used to have a bunch of .rule files, and now we have a bunch of .rule.m4 files that are used to generate rule files. So one M4 file generates one rule file. So the M4 file is like a unit of configuration right now. But you can really think of M4 as C preprocessor. So like simple things are simple, and I'm going to show you some difficult things to do in M4. So these are some fun examples, and the first one is a definition of a function. The first function discards a bunch of arguments, so it simulates the bash shift functionality, and to me it's quite hard to read, so I don't understand this very well. There is like a bunch of quotes and backticks, but you know, this is how you do it in M4. The second example is basically how you implement join function in Go, but this one is in M4, right? So yeah, so it's difficult to understand, and my colleagues seem to agree that it is. But you can still solve a lot of problems with M4, like not all of them. And we have deployed it. We are like relatively happy with it. But you can still see some repetitions inside our Prometheus config files. So you can see like we have 3 metrics, and we define a sum on these metrics, and we we basically sum these by some labels. So if you want to abstract this in M4, you would have to define a function that takes a list of metrics as an argument, then it takes a list of labels as an argument, and it outputs something. And this is considered difficult to do in M4, so we'll have to do a lot of magic to do this. So we are not doing it, and we have a bunch of repetitions there still. So this is one of the config frameworks we are using. And moving on, let's go to Kubernetes. So for those of you that don't know how Kubernetes works, it's like there is this new hype about microservices. Everyone is using microservices and Kubernetes. And if you want to run something on Kubernetes, you have to define a bunch of YAML files. And these YAML files define a Kubernetes resource. So what is a resource? A resource can be a configuration file. It can be a service definition, and the service definition says that here I have a service. The service runs on a bunch of ports, and it's running somewhere. You also define the resource requirements. So you say, like, here is my service. I want 3 replicas, and each service has, let's say, 1 CPU, and it's not going to go over this 1 CPU. So you have this bunch of YAML files, and we have decided not to write all these YAML files by ourselves. But we have decided to use a simple templating system that is based on text template, right? So on this slide, you can see the inputs into this templating system and outputs. So given service.yaml, and the service.yaml is a real YAML file, so it contains key value pairs. The key is like the name of the service, the image, the Docker image the service is running under, and resources and other things like this. And the other things you see there are the templates. So these files are named .yaml, but they are actually not YAML files. They are Go text templates. So if you interpolate all the variables inside service.yaml, inside these templates, you are going to get the outputs that are here. So you are going to get these generated outputs. So yeah, we have been able to abstract away a lot of repetition using this system, but we still weren't able to get rid of all of it. We have also considered using Helm, so if some of you know Helm, I can give you reasons after this talk, so you can talk to me later. But yeah, we have reasons, and we have decided not to use it in the end. So what's the problem with this approach? So it's based on text templates, and in Golang, text templates are not supposed to contain very serious logic. So you can have a bunch of ifs there, you can have some for loops, etc. But if you have something more complicated, like nested if statements and so on, these text templates are going to become very funny looking. So that's the problem. Also, I can give you some use cases that are a bit difficult to solve using this template system. So imagine that you are going to generate these files in all our clusters. So we have like EU1 prod cluster, EU1 testing, and so on. And let's say that you want to generate a service definition only for the testing and staging clusters. Then you have to modify your template file and add support to not generate configs for production clusters using some if statement, right? So the problem here is that you are modifying the templates themselves instead of the service where you have this requirement in. So what is going to happen, you are going to have a lot of features in this template, a lot of code in this template, and it's going to become a very complicated thing. Because the service.yaml, it just contains key value pairs, so you can't put a lot of logic inside that. That's one problem. Second thing is that we have different types of clusters. We have DC clusters, we have hub clusters, and we have some internal clusters. So the services, they are using a little bit different structure. So how does it fit here? So we have two options. Like we can define templates for hub clusters, DC clusters, and the internal clusters, or we can have like one template that contains like a lot of if statements, and it's able to like solve all our use cases. So both problems have some advantages and disadvantages. So if you have one big template, like good luck trying to modify it. If you have a lot of templates, there will be a lot of repetition. So yeah, so this this framework is nice even given all these problems, but you can still see some repetition there. Okay, so next one I'm going to talk about is Terraform. So for those of you who don't know how Terraform works, the most important command is the Terraform apply, and what it does, it reads the contents of the current directory. It reads all the .tf files, and this is basically considered a state you want to be in. And when you have this state, then Terraform is able to apply some changes. So what is Terraform used for? If you want to use GCE or AWS, you want to configure some file role rules, then you want to set up some like instances, instant templates, and so on. Like you don't want to click in the UI yourself and set it up yourself. So Terraform is used to provision resources in AWS or GCE. And this Terraform apply command finds out what is the difference between the system that is currently running or the configuration that is running on AWS and GCE, find the differences and apply those differences. So if you add some resources in your Terraform file, it is able to apply those resources in AWS or GCE. Right, so we will go to some examples, so you should see better like what it looks like. And yeah, here is actually the example. This is the structure we are currently using in our system. So all our Terraform stuff is defined in our clusters repository in the folder clusters, and we have a subfolder for every cluster in GCE and AWS that we are using. So you can see that we have like hub cluster named EU1, then EU2, and so on. And we have some subdirectories for each cluster. So we have a configuration for etcd master nodes. This is the master directory. Then we have the networking configuration for the whole cluster, and we have like a bunch of other directories. And you know, the unit of configuration here in Terraform is the directory. So you go to the directory, you run Terraform apply, and it will apply configuration for the whole unit you have there. So you know, the question can be, why don't we put everything, like the whole cluster definition, inside GCE-H-EU1? Why do we split it into separate parts? And the reason is damage limitation. So Terraform is a little bit unpredictable, and it used to be in the past. So imagine that you do some changes, and then you run Terraform apply, and then it will just destroy your cluster because you made some typo. It's a pretty unfortunate situation. So yes, so we have decided to split it in a separate parts. That's one thing. And also the other thing is that in the past, Terraform had some bugs where when you run Terraform apply, it destroyed all the firewall rules and recreated them again. So you get some time where you had no connectivity in your cluster. Like the things are changing and it may have improved. But running Terraform is a scary operation. Like you are doing a bunch of calls to GCE, and like who knows what might happen. So you should be careful. Right. So this is one of the Terraform files. This is actually what variables.tf looks like. And as you can see, it's just a bunch of boilerplates there. So nothing to see there. And this is used mostly to declare what variables we use inside some Terraform module. So if I go back, maybe, yeah. So so the module is master. The other, I think I should not call it the module, but let's call it the configuration unit. The config unit is master, another config unit is network. And in the variables TF, we declare variables that are needed by the module. And yeah, and here are the variables.tf. So let's go further. This is the this is what master.tf looks like, and it just imports a shared library. So it looks at /modules. It imports something, and it basically passes the variables from Terraform into that module. So apart from that import, it's just another bunch of boilerplate that we have there, and it's quite unnecessary. And also notice the GCE_base_file_ordered. So this is a funny thing. Terraform and HCL, it's a declarative language. So sometimes it doesn't respect ordering of resources. And this is like quite important for firewall rules, because if you mess up the ordering, it's going to delete your rules and do some stuff that it does not have to do, even though you have not changed your configs. So you have a hash map from string to string, and you use some features of HCL, then you can have these problems where config files are not really deterministic. So if you run Terraform apply, you get a bunch of changes that should not be there. So it's like one disadvantage of the Terraform that we have encountered while using it. Let's go. Okay. Yeah. Okay. Now we talk about Jsonnet. Yeah. Let's go back. Yeah. Okay. So let's talk about some more problems we have encountered. So imagine that you want to create a new cluster, right? So what do? Usually you copy paste some existing cluster, rename some variables, and change the network IP range and so on. But we also have some template directory that is named gce-h template. So we are thinking maybe you should copy the template directory, or maybe you should copy some existing cluster directory. So you don't really know what you should do. Like it looks like the correct approach would be to copy the template directory. But the problem here is that you don't really know if the template is up to date with the current stuff. Like people are committing a bunch of things into the repository, and you need to make sure that all of these things are consistent. So so you don't really know what to do there. But generally, when you create a new cluster in Terraform, you copy paste recursively, change some variables, and it should work. The real problem is that when you try to introduce a new variable to the system, you have to modify all the clusters, all the boilerplate that you have seen there, and apply these clusters yourself. Or imagine that you have a new library, you want to deploy a new set of etcd nodes into the cluster. You have to modify a lot of things to make this happen. So that's another problem. Okay. So Jsonnet is the last. Yeah, I think this is the last configurational language I'm going to be talking about. So Jsonnet is a bit similar to M4. It's not bad. It's not as bad as M4. But it basically takes a .jsonnet file and generates a JSON file from the JSonnet file. And JSonnet is just JSON with functions. And it's a very functionally oriented, so you can't really write procedures as far as I know. You have to write some functions in very functional style, so something like, similar to Haskell maybe. But anyways, the JSonnet file is the basic unit of configuration. And if you want JSON, like you have to have a JSonnet corresponding JSonnet file for that. And we are using this for our Grafana dashboards. So there has been a lot of repetition in these dashboards, and we have been able to solve or remove a lot of those repetitions by using Jsonnet. So it's fine. And I'm going to show you how it looks like. So this is an example. And here you can see that the Jsonnet looks almost like JSON, except the ingredients is an array of objects, and there is some kind of array comprehension. So we will have 3 objects inside this ingredients array. If you remove these ingredients completely, it would be valid JSON, well, except the quotes and the cocktails. So this part here, this is one object in Jsonnet, and there is a plus sign, and we are going to concatenate that object with another object we are going to generate. So let me show you. Yeah, and this is a new object, and it has a dynamic keys. So you will have 2 more keys. One is yellow screwdriver, and the other one is screwdriver. So you can see the for loop in the bottom, and the for loop will generate 2 keys with some contents, and this object will be concatenated to the parent object. So this is how Jsonnet works. You can have also libraries in Jsonnet, so we can include like a bunch of stuff, and we are using this. So what's the problem with Jsonnet? It's still a bit difficult to understand by engineers, so it's using completely different programming style, like the functional versus imperative one. 95% of the contributions are done by one person from Google as a 20% project. So if we decide to move to Jsonnet completely, we would be making some kind of a bet there. But on the other hand, it seems that there is one company that is developing some Kubernetes stuff on Jsonnet. So yeah, it would be a decision. And also the last problem is that everything is supposed to be a JSON, but for example, for Nginx or Elasticsearch, you don't have configuration in JSON. So this would not work for these cases. So what's wrong with all of this? So we have multiple approaches to solve our problem with configurations. And config formats are not ubiquitous around systems. So some things is using JSON, something YAMLs, and so on. Terraform is using like HCL or these Terraform files, but it's also compatible with JSON on the other hand. Yeah. So engineers have to hold a lot of stuff in their head. There is little editor support, lack of tooling, it's hard to unit test, and there is no feature parity between systems. So what is easy in one system is difficult in another, and vice versa. So what are we going to do about this? The question. So this was supposed to be the XKCD comic about standards. Yeah. So we have 14 standards. Let's create a new one, and we will have 15 standards. Yeah, obviously, we don't want that, but it's a joke. So, how did we solve this? This would be only 5th standard, so it's not 15, so it would not be that bad. But anyways, we were thinking about solution, and we have found out that you can't do complex logic in text template. It is supposed to be done in Go. So why not put all the logic inside Go, right? So we have decided to extract everything into the Go source code. So there are no YAMLs where you say like, these are my clusters, these are my services, but we have arrays in Go, right? There are no input text templates in a text format. We just put everything in Go strings. So this is the idea. And we have put all the configuration inside one binary. And when you execute this binary is going to generate all the configs for you for all the services. So this is the uniform system. And it can be dangerous because there is no like structure, conventions, or a safety net of a templating framework. So if you run an arbitrary code, you can get some funny results. You can do literally anything. There are side effects, there is non-determinism, you may get some random errors, and it may not be readable, but we have still decided to try this approach. And this is where we got. So this is the simplest program you can write in Playwright. So I'm going to go line by line. The main function is defining object PWIO. And PWIO is an abstraction over input and output. So you can write files using PWIO, you can read files using PWIO, but reading is done only for secrets and things that can't be inside the program or inside the repository. So you should not be reading files at all, just writing files. And you can think of PWIO as a big dictionary where key is a file name and value is contents of that file name. And you populate this dictionary, and then in the end, you dump all the files into disk using the dump files to disk method. And on the second line, you basically call pwio.withpath text, and you are saying that pwio should output all the files inside text subdirectory. So the call creates a new pwio object, but it will be linked to the old PWIO. They will be sharing the same dictionary of files. So if you run this program, it will output these files, right? So we will get these after running main.go. And now, right? Okay, demo time. So I'm going to give you a little demo here, so that you can actually see that it works and I'm not making stuff up. Right. Okay, so it is working. And here I'm going to show you my source code. So yeah, so this is the main file, and there is just a bunch of boilerplate. I'm defining two commands. One command is called the gen command, and it used to generate configuration, and the other command is the diff command. So when you like change configs, you want to diff like everything against everything else to see if your changes are correct. And yeah, I don't think there is anything interesting in main, but I have created this pwtest_kube file that generates some Kubernetes files, right? So the main.go is calling genconfigs, and genconfigs knows about three environments. One is testing, staging, and production. So this is fairly typical setup when you have some deployments. And the gen ES exporter function is generating a Kubernetes file via an API we have created for Playwright. So here, this one object is basically defining deployment, Kubernetes service, and a bunch of other things. So we don't need to work with multiple YAML files or multiple templates. Everything is defined in this one place. So let me actually run this. Right. So when I run the gen command, it is going to create a new directory, and it's this pwgen. So as you can see, it has created a directory for prod, staging, and testing. If you open testing, you can see deployment YAML and service YAML for ES exporter. It's some like random service I have taken out from our configs. And this is a legit Kubernetes config file. Then here you can see the service. It also supports the external DNS annotation. So if you put an annotation there, and if you have an external DNS spot running in your Kubernetes, it will register the DNS with Amazon. So we have this integration. And there is one more file that's called ES exporter YAML, and it just contains both files concatenated into one. So when you run kubectl, you can apply just this one file, and you don't have to apply like file by file. So if you have worked with Kubernetes, maybe you know the pain of deploying like all these files. Coming back to the source code. So you can see we have a gen deployment, true. It means that we want to generate the deployment YAML object. Then this tells Playwright to generate service object. And here is the actual output. So the kubeset has a method getOutputMap, and it will basically give you a list of like key value pairs. Key is the file name, and value is an object, and you can output them via output YAML, which is just wrapper around output file function in PWIO. And the last one, it's some other wrapper we have developed in PWIO that just outputs everything into this one file. Okay, so this was just intro like how it works, but I'm going to show you some interesting stuff here. So I'm going to show you the diffing functionality. So imagine that that in your testing environment you need only 100 milli CPU, but in production you want to use one CPU because you have a lot of users, right? So let's try to do it in Playwright. Oh, what did I do? Okay. Prod or production? Okay, prod. Alright, so this is a bit hacky way how to do this, but it's simple. You can see that it builds, and let's try to run this. So now this is a diff command, and I'm specifying the reference I want to diff against. So this is just the demo test branch with all the committed changes. So I'm diffing my uncommitted changes to the whole Playwright configuration that is committed inside that branch. So now it's checking out this repository inside current directory. in order to calculate the generated files, and then it calculates the generated files in my normal Playwright and just divs them. So as you can see, it seems to be working. So the ES exporter to the YAML has changed, which is the concat of service and deployment, and also the deployment has changed and it's colorized, but it's not something we have implemented, just color diff. Right. So this is the demo. So let's go back to the slides, I guess. Can we go back to the slides? No. Yeah. Cool. So we have the demo, and this is the structure in Playwright. Sorry. Right. So this is the structure. We have the main.go, which is the main entry point. So when you want to generate configs, you say like go run main.go, and it will generate everything. Then we have the pw in-out directory, which contains the pvio object that does the input and output. Then we have stanzas, and this is the lowest level stuff in Playwright. So it generates either strings or structures that are serializable to YAML or JSON. Then we have scribes. It puts together stanzas and outputs them into one text file. And then we have stage, and stage is the something like our own naming system. So we have a testing stage, staging, and production stage. So stanza is like the atomic thing. The scribe just takes stanzas together, and stage puts the whole thing together. PWGen contains the generated configs, and Playwright checkout is used for diffing like current state to anything you want. Some notable stanzas. So we know how to modify DNS records. We can generate Terraform configs for GCP, like load balancing, networking, firewall rules, forwarding rules. Then we have stanzas for Grafana dashboards, for Prometheus, Kubernetes that you have seen. Then we have something for Terraform that generates required version for Terraform. And so these are like the most interesting for us. And some features. So the configuration is completely deterministic, or at least we try to make it this way. And we have a unit test. So we generate config like 10 times, and if it's the same, then we say, oh, it passed the test. It doesn't mean that the configuration is deterministic, but it's probable that it is. All I/O goes through PVIO, and this is important for testing. So if you take out the PVIO and mock it, the whole Playwright is pure code, so it does not communicate with anything else. It should not do any syscalls apart from the context switching and stuff like this. But it's like a pure function you can test in isolation. So we are actually testing whether Playwright writes something, not via PVIO, but by clearing all the environment variables, changing the current directory, and so on. So it's a bit hacky. It doesn't test all the cases, but we are trying to make sure that people are not doing some nasty things inside. Yeah, but it's deterministic. Right, so before this slide, it has also one feature. So if you have some secrets outside of the repository, you need to read them, and not all the people have access to all the secrets. So we can generate configs that should contain secrets, even though you don't have access to those secrets. So you can diff everything. We are doing some hacks around that. And yeah. And then what needs to be done, we need to migrate all our configs to Playwright. So it's a long process. We have a lot of config frameworks, so it's slow thing. And then we want to open source it. We have not decided on timeline, but we want to give back to community and show it to people to see what they think about it. And this is it. So yeah, if you have some questions, feel free to ask. Yeah.
Have you come across the notion of configuration inheritance? It's maybe a bit of an anti-pattern, I don't know. But you kind of touched on it with how you handle the CPU, where you said, by default, I want this to be 100 millis, except if I'm in production, I want it to be 1. How does that notion of sort of what I see as inheritance scale? Do you find that's kind of at sort of 1 or 2 levels? The challenge I face is I have service level configuration, I have environment level configuration like you described, I have regional configuration, so if it's in Hong Kong it's this, UK this, Mexico that, and so on. And it very quickly becomes an absolute nightmare to manage. It looks like you could be heading towards the same thing. I don't know if you've come across that or not.
Yeah, so we have just started, and there are multiple approaches how to solve this problem. So currently we are passing Go structure from one function to another, and we are passing this function by value. So when you want to configure your service, you say like how much CPU do you want, what kind of image it is, and so on. And we have this object. We pass it by value into some other function, and this other function can modify this object. So there is some kind of an inheritance hierarchy. In some places, we are using the Go inheritance, so we are including structs inside structs. But we are not we are trying not to go into this like deep, nested hierarchy, because when you change something on top, it will change a bunch of things on the bottom. So we are still like exploring this problem, but we are trying to pass everything by value, so that when you call a function, you have a guarantee that the callee is not going to do any side effects that you don't expect it to do. Yeah, so like we have started, and this is the approach that we are taking. There is like some inheritance, some of this, some of that, and experiments, full of experiments. Yeah. Any other questions? Okay, no. So thank you for listening. I hope you enjoyed the talk.